So today we're looking at pose-free 3D Gaussian splatting via shape ray estimation. That's SHARE by no et al. From KAIST. And this one really tackled a huge bottleneck in 3D reconstruction. The camera pose problem.
It really does. The whole issue is that these amazing new 3D Gaussian splatting models, they're built on a very fragile assumption.
That you have perfect camera poses.
Exactly. And the second you step outside of a controlled lab setting, that data gets noisy, and the entire reconstruction can just, well, fall apart.
So SHARE's whole mission is to create a robust, high-quality, and importantly, feed-forward 3D GS that is genuinely pose-free.
And the way they do it is really clever. Instead of trying to guess the pose first and then do these error-prone 3D transformations, they solve for the shape and the relative pose at the same time by moving the whole alignment process into a high-dimensional Lady space. They build what they call a pose-aware canonical volume, which is guided by something called Plücker rays.
And then they refine that geometry with a new technique. Anchor-aligned Gaussian prediction.
Right. And the headline result here is that SHARE can handle real-world noise. We're talking errors of about 1 degree of rotation, and still blow past state-of-the-art methods that just collapse under that same noise. It's a massive step toward making 3D GS practical.
Okay, let's unpack that. Let's really get into this foundational challenge. Why are precise camera poses so critical in the first place? Why is relying on them such a bottleneck?
Well, the camera pose, its rotation and translation, is the geometric skeleton for the whole scene. It's the only thing that connects the 3D world to all those 2D pictures you took of it.
Right. If you don't know exactly where a photo was taken from, you have no idea how to map pixels from that photo back into a single, consistent 3D model.
Exactly. And the traditional way to get those poses is a pipeline, like structure from motion or SFM.
Which is notoriously fragile, especially for a generalizable system.
Oh, absolutely. If you have sparse views where the cameras are really far apart, what we call a wide baseline SFM just doesn't have enough information to find reliable matches.
But the real headache is that these things are done sequentially, right? You estimate the pose, then you reconstruct.
And that's the killer. Even a tiny error, I'm talking 1 degree rotation, a minuscule translation error, it leads to what the paper calls catastrophic geometry misalignment.
Can you give us a feel for what that catastrophe actually looks like? You know, for the folks listening who are actually building these things, what are the numbers?
The numbers are pretty stark. So let's take a top-tier pose-dependent method, something like MV-Splat, and run it on the DTU dataset.
Okay.
If you give it perfect ground truth poses, it gets a really good quality score, around 20.41 PSNR. But the moment the authors add just a tiny bit of Gaussian noise to those poses, a standard deviation of 0.05, that PSNR score just plummets.
How far?
Down to 12.84.
Wow, from over 20 to under 13.
Yeah, that's the difference between a high-fidelity model and, total geometric soup. It just shows how completely brittle and dependent these amazing 3D GS methods are. They're basically unusable where poses aren't perfect, which is everywhere in the real world.
And that's why pose-free has been such a chase. We've seen some attempts before, right? Mostly built on NeRF.
Exactly. You had methods like CopoNeRF and LEAP, but because they're based on NeRF, they usually end up with really long inference time, sometimes minutes for a single scene, or these really complicated joint optimization loops.
Which kind of defeats the purpose. The whole promise of Gaussian splatting was speed over NeRF.
Precisely. So SHARE is designed to bring that critical robustness directly into the fast 3D GS world.
Okay, so that brings us to the core innovation. How does SHARE sidestep this whole fragile process of estimate then map? You're saying it avoids explicit 3D transformation?
That is the key philosophical shift. The problem with the old way is you take points from view A, you rigidly transform them with your noisy pose, and then you try to match them to view B. If the pose is bad, the alignment's bad. Simple as that.
So what does SHARE do instead?
It flips the script. Instead of aligning 3D structures, they unify the features from all the different views first in this high-dimensional latent space. They build one single fused canonical cost volume that has all the information.
And only then do they try to figure out the 3D Gaussians from that unified representation.
That's it. You move the problem from rigid, brittle geometry into a flexible, learned feature space. And that gives you massive resilience against noise.
That makes a lot of sense intuitively. You're letting the network's learned features do the heavy lifting for alignment, not some shaky transformation matrix. But isn't that computationally expensive? I mean, are you trading the speed of 3D GS for this robustness?
That is a fair and absolutely critical question. They get around this by making sure the whole framework is feed-forward, no slow optimization loops, and by designing it in two really efficient modules.
Okay, what are they?
First, you have the ray-guided multi-view fusion, then you have the anchor-aligned dense Gaussian prediction. And the fusion part is done cleverly with patchwise attention, not some global brute force search.
Let's dig into that fusion part. This is where they're estimating features and pose information at the same time. How is that pose info encoded?
So the network starts with a matching transformer to pull out the multi-view features, let's call them FI, but at the same time, another lightweight transformer is estimating the camera poses. And here's the trick.
Okay.
It doesn't output a standard rotation and translation matrix. It encodes the pose as patchwise, Plücker rays.
Plücker rays. Okay, that sounds pretty mathematical. Why is that a better way to represent a pose for this task?
Okay, so think about it like this. A standard transformation matrix defines the pose for the entire camera as one single rigid block. If your estimate is a tiny bit off, that entire block gets warped incorrectly.
Right, the whole view is wrong.
But a Plücker ray just defines a line in 3D space. The network here predicts a whole bundle of these rays, encoding the view origins and directions on a pixel-by-pixel or patch-by-patch basis. So instead of one big, noisy global transformation,
you have thousands of tiny local geometric guides.
You've got it. It's like having these little local beacons for every feature patch. It provides a geometric bias that's just so much more robust for alignment. It allows for tiny local corrections.
So the Plücker rays are this granular, more trustworthy representation of the geometry. Once the network has those rays and the 2D features, how does it actually build that pose-aware cost volume you mentioned?
They start with a classic idea from multi-view stereo, MVS. They build an initial set of cost volumes by just projecting the 2D features out along a bunch of hypothetical depth planes. It's a way to start thinking in 3D.
But that's just a coarse first step.
Exactly. The real secret sauce is the refinement. These initial volumes get refined using cost aggregation that is specifically conditioned on those predicted Plücker rays using patchwise cross-attention.
So the network is using the local rays to check if the features it's trying to merge from different views are actually geometrically consistent. The rays are injecting the spatial relationship right into the feature matching.
Precisely. It's embedding that geometric awareness directly into the features. This process results in two final canonical volumes: a geometry volume, BG, for the coarse shape, and a feature volume, V, that holds all the fine-grained visual detail.
And those two volumes are then passed to the second module, anchor-aligned dense Gaussian prediction. So, if the geometry volume is already pose-aware, why do you need another prediction step?
Because the geometry you get straight from a cost volume is always a bit coarse. It's inherently smooth. It struggles with sharp corners, edges, fine details. If you just predicted your Gaussians from that, the result would look kind of blobby. You need a coarse-defined strategy.
And that's what the anchors and offsets are for. They're the refinement step.
Yes. So step one is coarse anchor estimation. The network looks at the geometry volume, VG, and calculates a coarse depth for each pixel ray. That defines the initial 3D anchor position. You can think of this anchor as the network's first confident but low-resolution guess for where that point is in space.
Okay, so that gives you a center point in 3D for every pixel. How do the offsets refine that?
This is the fine detail part. For each of those single coarse anchors, the model then predicts, say, k different offset vectors using the high-res feature volume, Vieta. The final super precise Gaussian mean is just the anchor position plus one of those offsets.
So visually, instead of putting one Gaussian at the coarse anchor spot, it puts the anchor down and then scatters a few more Gaussians in the immediate vicinity based on those offsets.
That's the perfect mental model. The offsets let the network sample the space right around that coarse guess. It learns to estimate multiple distinct geometric details. For example, if the anchor lands just behind a sharp edge, one offset can push a Gaussian forward to capture the true edge, while another captures texture right behind it.
And then it predicts all the other Gaussian parameters, color, opacity, and so on from there.
Yep, based on the offset and the feature volume.
Yeah.
And the ablation study they did really shows how critical this is. The model with just the anchor-only prediction, it gets a really low 14.05 PSNR on DTU. But when they use k equals 3 offsets, the performance just jumps to 19.36 PSNR. That 5-point leap tells you this local refinement is absolutely essential for getting that high-fidelity result.
Let's get to the empirical results then, because that's where the rubber meets the road. They tested this on small objects in DTU and also large-scale videos in real estate 10K. What were the big takeaways on robustness?
The DTU test is, for me, the most compelling result. Remember how we said MB Splat crashed from 20.41 PSNR down to 12.84 with just a little noise?
Yeah.
Okay, so now look at Share. Using its own internally predicted poses, it scores 19.36 PSNR. Meanwhile, MB Splat, when it's forced to use those same kinds of estimated noisy poses from an SFM system, only gets 13.96.
That's an incredible difference, almost 6 PSNR points higher.
It's a huge gap. It shows that Share, by solving pose and shape together, is just fundamentally more resilient. It's learned to handle the exact kind of small inaccuracies that completely cripple the traditional methods.
And what about scalability? How did it handle something huge and complex like the real estate 10K dataset?
It held up great. On real estate 10K, which has, entire rooms and video motion, Share got the highest scores across the board, 21.23 PSNR. And importantly, it beat the pose-free nerve methods like Coponer F, which was back at 19.54.
So it scales, and it keeps the speed and quality advantages of Gaussian splatting.
Exactly. And it's not just about handling noise. It's about true generalization. They ran cross-dataset test training on one dataset, testing on a totally different one.
Like real estate to acid.
Right. And it showed really robust performance, confirming that it's a genuinely generalizable feed-forward solution. It's learning fundamental principles of alignment, not just memorizing a dataset. And you don't need any test time optimization, which is a huge barrier for a lot of methods.
So just to quickly revisit the architecture, the ablations really proved the value of their two big ideas. What happened when they tried to remove the Plücker guidance?
The moment you take that out, you see immediate severe geometric problems. The PSNR dropped from 19.36 straight down to 17.52.
So that confirms that geometric bias is essential. You can't just fuse features blindly.
Not at all.
Yeah.
The canonical volume has to be pose-aware. And on the other side, the power of the offset prediction is just as clear.
Right, that jump from 14 PSNR with just the anchor to over 19 with 3 offsets?
Absolutely. It proves that this course-defined strategy, a rough anchor plus learned detailed offsets, is a really effective way to pull high-resolution structure out of a learned feature volume without ever needing a perfect pose to begin with.
So to sum this all up, Share really does seem to provide an efficient, scalable path for robust 3D reconstruction with Gaussian splatting. It's moving the whole problem of alignment away from these fragile 3D transformations.
And into this much more resilient, latent space feature fusion guided by those Plücker rays. It changes the core problem from we have to get the pose right first to we can bake the pose uncertainty right into our feature fusion engine. That's a huge paradigm shift.
It really makes 3DGS feel much more practical for, say, mobile phone captures or any uncalibrated scenario.
For sure. Now, the authors did point out one potential limitation, and is a tough one that affects pretty much all multi-view systems.
And what's that?
They noted that performance can still struggle in scenes that have minimal view overlap. So think of extremely sparse 360-degree captures where the cameras are just really far apart from each other.
That's always the hardest problem. If there's barely any shared information between views, it's hard to build that strong canonical volume in the first place.
Even with the Plücker ray guidance, it's a struggle. And this really poses a fascinating question for future work. What kind of architectural changes could make that fusion module even more robust for those extreme sparse-view cases?
Maybe something more than just local patch matching, some kind of global attention, or even injecting semantic knowledge about the scene when the geometry is just too ambiguous.
That's a great thought. It's definitely something for researchers to think about as they keep pushing the boundaries on what's possible with truly robust, pose-free 3D capture.